Hello everyone, here's our notes for 1.5, the law of conservation of energy. So the law of conservation of energy is that energy can neither be created nor destroyed, it can only change location or form. So changing location, that is you're transferring it somewhere, so our heat transfer. So remember either conduction, convection, or radiation. So changing location or changing form. So in this unit, it's also going to be known as the principle of heat exchange. So our principle of heat exchange. Let's say I take this sword, I put it into the fire until it's red hot, I raise its temperature, and then I put it into this bucket, or beaker in this case, of water. Okay, so what is going to happen to the water? Well, it's going to raise in temperature. So it's going to gain heat from our sword. Remember that the heat lost by one object is going to be gained by the second one. So sword was hot, taking that heat, putting it into the water, so transferring that heat to the water. So if I think about my two objects, so object one, let's say, is our sword, and object two is our water. So the sword, once I combine it with the water, so after it's been in the fire, I'm combining it with the water, your sword is going to lose heat. So it was hot, it's going to be losing heat. Okay, and it's going to be losing the same amount of heat that the water is gaining. Well, the water and the air, but we're not counting the air or anything. In our physics examples, all the heat from one object gets lost to the other object. So for our sword, it's losing heat. Remember, to show that I'm losing heat, I can write it as negative. So the heat lost by the sword is going to be the heat gained by the water. They're not going to raise the same temperature or lower the same temperature, but the heat will be the same. So the heat lost by one, not the temperature difference, the heat lost by one will be the heat gained by the other one. So heat lost equals heat gained. Okay. Now this is going to happen until the sword and the water end up reaching what's called thermal equilibrium. So thermal equilibrium is when our heat, or our temperature, sorry, is going to be the same. It'll be equal. Okay, so thermal equilibrium is when the temperature of both of your objects reaches the same temperature. So when both objects reach the same temperature, we've reached thermal equilibrium. At that point, the sword is not going to cool down anymore because there is no more temperature difference. So the sword is going to be the same temperature as the water. The water is not going to heat up anymore because it's the same temperature as the sword. There's no temperature difference. No more heat can be transferred. Okay, remember, in order for heat to transfer, you need a temperature difference first. Okay, so thermal equilibrium. So two objects in a system will reach a balance with each other. So they will reach the same temperature. Okay, so temperature 1 of water, temperature 1 of sword, and there will be a final temperature of the water and the sword. So there's going to be, in the formula that we are going to make next, initial temperature for the water, so what the water was initially at, an initial temperature for the sword, what the sword was initially at, and the final temperature will be what the water and the sword reach. So they reach thermal equilibrium. They will reach the same final temperature. So originally you have your hot sword mixing with your cold object. Now remember, the hot object has a lot of energy to give off, so its atoms are going to bump against those in the cold object and speed them up. Okay, so the cold object's atoms will start moving faster and faster. Okay, and this will happen until they reach the same temperature. So all of their molecules or atoms are moving at on average at the same speed. So putting the principle of heat exchange into a formula so we can actually do some stuff with it. So just from our previous slide, we have our heat lost equals our heat gained. So negative Q equals positive Q. Now we're lazy scientists, so we do not need to write positives in front of things. We already know and assume that they are positive. Okay, so here we have for our first object. Here we have for our second object. So the heat lost by one object will be the heat gained by another. So what is the formula for heat? Well, if I think back to the last lesson, to specific heat exchange, the heat lost or gained by an object has to do with whatever the mass of the object is, whatever the object's made of, and the change in temperature for that object. Okay, so same thing for this object. It will depend on its own mass, its own specific heat, and its own change in temperature. Now, it's going to be confusing if I just have this as M and this is M. So this is my M for object 1, my specific heat capacity for object 1, and the change in temperature for object 1. Same thing here. This is the mass of object 2, specific heat capacity of object 2. I'm talking about two different things, right? And my change in temperature for object 2. And don't forget that one of these is losing heat. Okay, so negative M1C1 delta T1 equals positive M2C2 delta T2. This is our formula. Okay, so the heat lost by one object is going to be gained by another object, where I'm just defining our variables. Okay, so M1's mass of object 1, C1 specific heat capacity of object 1, delta T1 change in temperature of object 1. Mass still measured in kilograms, C still measured in kilograms per, joules per kilogram degree Celsius. Okay, and your change in temperature is still in degrees Celsius, or sometimes, once again, you'll see it degree Kelvin, but usually degrees Celsius. Okay, so kilogram joules per kilogram degree Celsius and degree Celsius. Now make a note for yourself. So remember delta T is T2 minus T1. Now T2 for object 1 is going to be the same as object 2. So the final temperature of object 1 and object 2 are going to be the same. Okay, so the final temperature of object 1 will be the same as the final temperature of object 2. So T2 for object 1 is going to be the same as T2 for object 2. That's going to be important to remember. I guarantee that will mess some people up. Okay. So lecture example 6. We have a 0.2 kilogram piece of iron at 340 degrees Celsius. It's cooled by placing it in water at 22 degrees Celsius. So how much water is needed if the mixture reaches a final temperature of 24 degrees Celsius? So breaking this down, so we have a 0.2 kilogram piece of iron. Okay, so let's break up our givens right away into givens for iron and givens for water. Okay, so for iron and for water. So for iron, I'm going to need an M, a C, and a delta T. And instead of using ones, I'm going to use a subscript that makes sense for iron specifically, so that when I'm substituting into my equation, I'm not getting myself confused. So I'm going to use I for iron. When I'm doing water, I'm going to use W. So water, water, water. So the mass of my iron is 0.2 kilograms. And it is at 340 degrees Celsius. So this is the mass of my iron. This is the initial temperature of my iron. So T1I. Sorry. Yeah. There. Okay. So here's the thing. My delta T is my T2 minus T1. So I know T1. I know my initial temperature of my iron, okay, is 340 degrees Celsius. Okay, so taking a look, going next is cooled by placing it in water that is 22 degrees Celsius. Okay, so this is the temperature, initial temperature of my water. Okay, so once again, I'm not given a change in temperature, I'm given an initial temperature of my water is 22 degrees Celsius. So how much water is needed? So I'm looking for the mass of water. If the mixture reaches a final temperature of 24 degrees Celsius. Okay, so I have my iron and water mixing, and they reach a final temperature of 24 degrees Celsius. That is temperature 2. For which one? For both. Remember, they are reaching the same final temperature. So iron is going from 340 to 24, and water is going from 22 to 24. So the change in temperature of my iron, so my TF is 24 degrees Celsius. Remember, it's the same for both. So my final temperature is 24 degrees Celsius, so calculating our change in temperature. So final temperature is 24 degrees Celsius minus 340. And my change in temperature for water was, so it reaches 24 degrees Celsius minus 22, so T2 minus T1. So water, 24 minus 22, changes in temperature by gaining 2 degrees Celsius, so it gets 2 degrees Celsius hotter. Our iron, on the other hand, does not. Okay, so remember, it's important to know that your heat lost is your heat gained, not your temperature lost is your temperature gained. Okay, so keep that in mind. So iron isn't losing 2 degrees Celsius of temperature, it's losing the same amount of heat, but since iron is a poor insulator, it's a really good conductor, it will lose and gain heat really quickly. Okay, so we get negative 316 degrees Celsius for the change in temperature of our iron. So remember, negative just means lost heat, positive gained heat. All right, so we almost have everything ready to put into our formula. So when we're using this formula, there only needs, or any formula, you should only have one thing that you're looking for. Otherwise, you have more manipulating to do, and it's annoying. But as soon as you see that you're missing some constants, remember, we get these from our table. So here we go. Our water, if you haven't memorized it already, is 4,180. Iron is 450 for C. 4,180 joules per kilogram degree Celsius and 450 joules per kilogram degree Celsius. Okay, sorry, it's so messy right now. Okay, so remember, first step, do our givens. Second step, write out our formula. So negative M1C1 delta T1, but I changed this into iron and water. So MiCi delta Ti equals M2C2 delta T2, or MWCW delta TW. See how the way I set up my question corresponds with the way I'm going to substitute into my question. Okay, so here I'll have my iron stuff, here I'll have my water stuff. Now, it doesn't matter which side this negative is on. I like to keep it on the side that will have the negative temperature change, just because then it cancels out, and like negative times a negative will equal a positive, and you don't have to worry about dividing by negative or anything. But honestly, it doesn't matter mathematically which side the negative goes on if you have it with your water or your iron. I like to, for my own purposes, keep it with whatever is losing heat, so our iron. But once again, do not have to. So here's our formula. Let's solve for the variable we're looking for. Isolate the variable, and then substitute it in and solve. Okay, so looking for the mass of our water, so divide by CW and divide by delta T. Okay, so reduce, reduce, left with the mass of my water. So negative MICI delta TI divided by CW delta TW. So variables isolated, I can now sub in and solve. So negative, then MI is 0.2 kilograms, CI 450 joules per kilogram degree Celsius, and delta TI is negative 316 degrees Celsius. Okay, divided by, now water's information will go on the bottom. So C of water is 4,180 joules per kilogram degree Celsius. And my delta T of water is positive 2 degrees Celsius. Now, taking a look at our units, I have degrees Celsius, reducing with degrees Celsius. I have a joules per kilogram degree Celsius on the top and a joules per kilogram degree Celsius on the bottom, so that's all gone. And I'm left with kilograms. Now, here's a nice thing about this formula is, remember how we always had to have our mass in kilograms before in our specific heat capacity? Well, here you'll just end up with the units that you were, the mass units you were given if you're solving for mass. So you don't necessarily have to change it to kilograms. I still suggest changing it to kilograms because the more you do that, the more you just remember for other formulas you do need to. So I will usually almost always change my mass to kilograms anyway, okay? But just know that you do not necessarily have to. Oops. Okay, so once again, watch out with your calculator. If you are trying to put this all in at once, okay, so negative 0.2 times 450 times negative 316, negative times a negative is a positive, so you should end up with a positive answer, for one thing, if you're putting it in correctly. And divided by 4,180, but you're also dividing by 2, so don't do divide by 4,180 times 2, because that will take whatever you get here and then multiply it by 2 instead of divide it by 2. So either do divide by in your calculator or put the whole bottom in brackets. Honestly, guys, you make more mistakes with using those brackets. I see it all the time. Stop trying to use so many brackets. Okay, just divide by. Just do it. Okay, and you end up getting my rant. So into your calculator, making sure you're doing it correctly. So doing this with me, 3.40198, so on and so forth, and taking a look to see what we need to, how many significant figures we need. So we have 3 here, 2 here, 2 here, 2 here. I will need to, since this is multiplication, round to 2 significant figures. So 1, 2, cutting off here, take a peek over the wall. Oh, it's a 0, so it's going to stay the same. So the mass of my water, oops, so the mass of my water is 3.4, and remember our units we ended up with were kilograms. Okay, so checking that we answered the question, how much water is needed if the mixture reaches a final temperature? So if I'm given 0.2 kilograms of iron, I need 3.4 kilograms of water. Okay, now this is easy for solving for, or this is the method you'll use to solve for any of these variables. So if I'm solving for MI or delta TI or MW or delta TW, change in temperatures, but it's not going to work if you're looking for the final temperature. So in order to find the final temperature, we go through these steps in order to isolate our variable. to get to this answer. So our final temperature of our water will be MWCW T, our initial temperature of our water, plus M2C2, an initial temperature of our second thing, so like our iron for this case, divided by MWCW plus M2C2. So here's, I'm not going to make you do this every time. So I'm just going to give you this formula. It's not that hard. You do have to do some factoring, and like removing a greatest common factor. Sorry. And I'm not going to make you do it every time. So I will give you this formula. Given, you're welcome. Okay, so the equation solved for T2 is, so T2 equals M1C1 initial temperature 1. So in this case, the I means initial. Okay, so initial temperature and initial temperature 2. Okay, and divided by M1C1 plus M2C2. And you only use this equation if you need to find your final temperature. Only. So if you have to find your final temperature and you're given two objects, so putting iron into water, you have the information for two objects, you only use this equation if you're finding the final temperature. Anything else you use are just regular equation. This is that equation solved for final temperature. Okay, so don't try to use this for finding like your mass or like a specific heat capacity. Don't do it. This is just for finding final temperature. Okay, so lecture example 7, we have a 0.5 kilograms of water, okay, mixing with 0.2 kilograms of water at 20 degrees Celsius. What? So this water is 50 degrees Celsius. There's this much of it. This water is this degree Celsius with this much of it. So I have water 1 and water 2. Okay, so M1, C1, M2, C2, and we have initial temperatures, so T initial 1 and T initial 2. Okay, so my mass of my first water is 0.5 kilograms, and its initial temperature is 50 degrees Celsius. The C of water is 4,180 joules per kilogram degree Celsius, which will be the same for my second one, since it's still water. What's different though is we have 0.2 kilograms of it, and it is starting off at an initial temperature of 20 degrees Celsius. Okay, all of our information. Now I'm finding the final temperature, so I will not be using this formula because it's not solved for final temperature. This will take too long. I would have to go through all of these steps to isolate that variable, so I will use the formula that I gave you for finding final temperature, this formula. All right, so T2 equals M1 C1 delta T1 plus M2 C2 delta T, or not delta T, come on, Hardy. Initial 1, initial 2, there we go, sorry. And then M1 C1 plus M2 C2. Scheiße. Okay, solved for final temperature already. And now we just have to sub in. So equals, I'm going to pause it. Okay, so substitute in M1 C1 initial T1, M2 C2 initial T2, M1 C1. So this one and this one should be exactly the same, plus this one and this one. All right, now into our calculator it goes. Once again, if you're going to put this all in at once, make sure that you are putting the whole denominator into brackets. And for this one, you will also need to put the whole numerator in brackets. So it does this value plus this value and then divides that whole thing by the sum of these two values. If you don't put that all in brackets, then it will just divide this one, your second term, by this. So I would suggest doing this, adding it to this, equaling it, and then dividing by then 0.5 times 4180 plus 0.5 times 4180, all in brackets. Okay, if you need help with your calculator steps, please come see me and I will help you out. I won't go into it more here. Besides, tell you to watch out. So you should be getting the answer of 41.4285, so on and so forth, degrees Celsius. If you've put everything into your calculator correctly. If not, come see me or ask a friend. Now, taking a look at our information for our sig figs. So 2 here, 3 here, 2 here, 3 here. So we need two significant figures. So cutting off at the 41, taking a peek over, this will be our final temperature is 41 degrees Celsius. Good. And we're done. Okay. So we are going to be doing a lab with this. We're going to be using something very similar to this, so a calorimeter, and it is an insulated container that has a thermometer that measures the temperature. We will be putting a bar of metal into this, and it will be insulated, so hopefully very little heat will be released into the surrounding environment, so it all stays inside. There will be water inside. We will be putting our hot bit of metal in, and we will be finding out what the specific heat capacity of that metal is. Doesn't that sound like fun? Okay, yes, it does. All right, so your assignment is page 321, number 6 to 9. Good luck.